Thank you. My name is Chris Wendt. I work for Comcast, and I have also been very heavily involved in the standards work around some of the mechanisms that are being proposed to help curb the call spam and illegitimate robocalling problem that I'm sure everybody is aware of. I am one of the authors of some of the IETF drafts that are available, and I'm also co-chair of the ATIS SIP Forum NNI Task Force that's been heavily involved in this issue as well. And I'm also participating in the recently announced robocall strike force. So I'm sure everybody is aware the telephone network is a complex set of interconnecting devices. We see calls coming from both analog and IP-based devices. And that is a good thing in the sense that it's allowed the ecosystem to evolve as part of making it as flexible as possible to initiate communications onto the telephone network. But obviously, bad actors can take advantage of some of those good things that we put into the network, and we've seen that lately. The focus of today's talk is going to be the VoIP network itself. So many of the standards we're talking about are part of specific to VoIP rather than the SS7 TDM world. Really, that equipment hasn't been touched in a long time, and it's very hard to go back and revisit those protocols. But the good news is, in the cable world, a vast majority of the cable world has already moved to SIP and VoIP. And in the mobile world, there's currently an effort to move all of the cellular devices over to VoLTE, which is end-to-end SIP. So the focus we've decided to, that's why we've decided that the IP VoIP world is where we should focus our efforts, because it's where we're moving in the future. And there's also initiatives to push folks to move to sunset the BSD network in general. Another initiative that's going on is Google and Apple on mobile devices are starting to put some hooks in for supporting call spam warnings. In the cable world, caller ID to the TV would also be another place that could help alert users of potential spam. But to assist those, putting something in the network that can assist end devices to make a better determination or provide specific validation of the caller would be helpful, and maybe also provide some consumer benefit. So obviously, if your bank or your doctor is calling you, you want to be sure that that's actually them calling you. So from a standards perspective, there's been coordination between a number of standards groups. As I mentioned, IETF STIR is a working group in IETF that's focused on defining the core protocols and technologies being applied. In ATIS SIP Forum NNI Task Force, we have a framework we're calling Shaken to correspond to the STIR effort. And this is focused from a service provider perspective on how we're going to put STIR technologies into the network and how we're going to deploy them. And there's also some 3GPP involvement for some of the mobile device specific specifications for how we deliver the verification information. So I have an overview diagram at the bottom there. It's sort of just a basic thing if you haven't been looking at this and it's all brand new to you. One way to think about these technologies is sort of like a PKI. You know, in your web browser, when you go to your bank, you want to be sure that you're talking to the bank website. So there's public keys and private keys that are used to make an association, a validated association with the content that's being served to you and the connection that's being served over. That's sort of a corollary to what STIR is doing. So when a call is initiated, it'll go through something called the STIR Authentication service, which will sign the call and the identities that are in the call. And this has to be at some authoritative part of the network. And then when the call is delivered through the telephone network to the end provider, for example, there's a verification service that will get the certificate that's associated in the signature, and then verify that cryptographically, verify that it's a trusted certificate, and then verify the call and deliver it to the end user. So to get a little deeper, in IETF, there's 3 main standards in the STIR working group. Passport. Passport is the document that defines the digital signature. It happens to use something called JSON Web Tokens. There's RFC 4474 BIS, which defines specifically the SIP usage of Passport. And then there's a certificate usage document, which defines how certificates should be used in the STIR protocols. And then there's 2 new documents that have been submitted into the dispatch working group. One for call info and to identify and label calls, and Henning has submitted both of these. The other is a spec for defining a unwanted call response code, something he's been talking about for a while, 666 as the response code. From the ATIS and 3GPP standards point of view, we have just completed the Shaken framework. So as I said, this is the framework that defines all of the deployment specific wrappers that we need to put around to getting deployment into the network and over our NNI peering points. It defines a little more specifically what the authentication service and verification should be doing, what should be included, some general guidelines. We'll also be working on a best practices document and use case document to define what happens in certain network scenarios. And there's also a certificate framework document that we have initiated and target for the end of the year that'll define the initial certificate management and administration. So a big part of STIR is obviously the management of how we provide the certificates, what the certificates look like, and how they're used, and how they're secured and governed as well. So this document will point to that. And then in 3GPP, like I said, there's some specific, there's a specific Veristat parameter defined for 3GPP handsets to use that the verification service would apply once the verification is successful. So Passport, this is the base level object that is being used. As I mentioned, it uses JSON Web Token. And basically what it is a JSON object that has a signature. So it has a defined way of defining what the cryptographic algorithm being used to sign the token, a pointer to the public key certificate that can be used to validate the token, And then the main part of it is the claims. So in a token, you make some claims, and then the claims in Passport are specific to IP communications. So there's a originating identity and a destination identity, and we also mandate a date as well. So part of it, the originating identity is the main thing we want to protect and validate, but the destination and date are important to make sure that people aren't taking these tokens and doing replay attacks and saying, hey, I'm coming from Chris Wendt's cell phone and he's calling everybody in the world. Another nice part of Passport that we've built in is the ability to add extensions. So beyond those base claims, we add the ability to claim other things, and potential things that have already been talked about are including the verification of CNAM, or also using it for government priority calls to validate that you typed in the correct password and you are a valid user of the GET system. The signature itself is a standard JWS X509 based digital signature. So we have a specific canonization format for all of the header and claims objects. This guarantees that, well, it supports two things. One is we have a full and a compact form. Compact form is mostly just to save the bytes transmitted, but we want something consistent so that the signature stays valid whether you're using full or compact form. And we also use elliptic curve prime 256 algorithms, and the sample that I'm showing here is an example of that token sort of formatted into, they're all base 64 encoded, that's why it looks like gobbledygook, but the first section is the header, the second section is the claims, and then the third section is the signature itself. And JWT is being used a lot, not just for this, it's been used a lot in authentication and authorization type applications on the web as well, so it makes a lot of sense to be using that. So for RFC 4474 BIS is how Passport is being used in SIP message. There was a RFC 4474, but it was depreciated. For this work, it signed actually the entire invite, and as probably most people in this room know, SBCs on the SIP network generally like to change the invite, so there was issues with that. So 4474 BIS defines specifically, as I mentioned, signing the critical information that we want to preserve and validate, which are the originating identity, destination identity, and the date. 4474 BIS defines a new identity header. There used to be identity and identity info, but now we've consolidated everything to the identity header. And this, by default, includes the Passport signature as the first object on the identity header, and then it includes other information that's used to reconstruct the token itself. So the URL for the public key certificate, as well as the algorithm that's being used. And then, as I said, authentication service and verification service are the logical components that will validate these and are defined in 4474 BIS, actually. So here's a quick sample of how you map things between the Passport token and the SIP message. There's algorithm, the type is defined, will be registered in IANA as Passport. And then the X5U is the JWT way of, or actually JWS way of saying which the URL to get the public key certificate. And then IAT is the, I think it stands for initiated at time. So that corresponds to the date header. And the, oh, actually I didn't update those claims. Now they're DEST and ORIG are the claims for the originating telephone number and the destination telephone number. So more details about the Shaken framework. So like I said, we took the STIR specifications and we started working on the framework for how we actually get this thing into the network. One of the big big initiatives that we wanted to make sure we could do is to keep it as simple as possible so that there isn't too much barrier to put it in the network and promote interoperability and interworking. So we focused a lot on that. We wanted to make sure that there's not too many certificates to manage. We wanted to make sure that everything is consistent. We wanted to make sure that, you know, typical SBC deployments and other things aren't going to play too much in breaking any call flows. So we took a very multi-pronged effort into looking at all these different angles. And the intent here for Shaken is that it will evolve. It's not going to be a static document. As initial deployments get out, we will go back and evolve the capabilities of the network and make sure, you know, and also provide feedback on how we're doing in terms of solving the spam calls problems that we're seeing, and make sure that all the use cases are covered. But initially, we're looking at the basic use cases, and then as time goes on, we will evolve them to support all the other ones. So we have a reference architecture defined in the Shaken document. It's sort of 3GPP based, but that doesn't necessarily mean, and we make it clear in the document, that doesn't mean that you have to be a 3GPP architecture to support this. Basically, you have at the top there the certificate creation and provisioning. The TNCR is where the public key certificate, these are all logical components, by the way. This shouldn't follow this necessarily as a pure implementation diagram. So the certificate repository was where service provider would store their public key certificates. And then if you're familiar with IMS, our 3GPP IMS diagrams, you have the SIP UA, the CSCF is a routing function, and then the access SBC is the IBCF and transit gateway. And then STIAS is the authentication service. It talks to a logical key store that would, you know, securely store your private keys. You don't want to make sure those don't get out in the wild. And then on the other side, the STIBS, the verification service, will talk to the certificate repository in order to get the public key certificates to validate the signature. So one of the, probably one of the bigger things we've defined in Shaken is a passport extension. So I mentioned that passport can be extended. So the use case that we're working on initially is the case where a service provider has basically one or a few certificates that they're managing to represent their origination of telephone calls. And within that framework, we needed to provide some sense to the other side of how that call was originated. So as you know, Service providers may have direct customers like UE devices that they manage that are initiating calls. They might have wholesale or chunk services that they get calls from their customers, or they might be providing transit services where the calls are coming into the network from unknown origination. So we have attestations that we've created to cover those exact scenarios. So the first one is full attestation, where you know the caller, you know the telephone number that they're using, and you've fully attested to both in the token. The second one is a little bit of a variation of that. You know the caller and where the call was originated from, but the call is using a telephone number that you either do not have authoritative rights to, or the customer has not validated with you. And then the third one is purely, I got this call through some transit network, some gateway, and I know nothing about it, but I want to sign it because this is the point where it originated onto the VoIP network. And that's useful for things like traceback and other things that I'll talk about a little bit on the next item. The next claim that we're adding is originating identifier. So this is meant to be a unique and opaque identifier that the originating provider would associate with the call. And this really is specifically, well, it's actually used for two different things. One is it can identify the exact point in the network. It's supposed to correspond with a node or a customer or something that defines a certain set of where calls are originated, so that for a traceback it can be used to identify potentially when a call is reported as fraudulent, you can find out where that call exactly originated, even within a service provider that originated it. And then the other use for this is for potential analytics types functions that can identify potential bad actors that are sending calls in certain patterns or other things, and the originating identity can help guide it to say, well, I see some weird behavior happening here, and it has this originating identity that's common, so this is probably a guy that maybe I should maybe first the service provider should make sure they're doing legitimate things. So this is an example passport extension, passport with the shaken extension. And really the things that are added here are the PPT shaken in the header to identify that it has a shaken extension, and then the two new parameters, attest and orig ID. The next part of shaken that I mentioned is the certificate management side. So we have to make sure that we manage our certificates correctly, and if you know anything about X509, it has the ability to, as most web PKI does, you have a certificate authority that represents the trust anchor or the trust in the system. So service provider can't just claim that they have the ability to originate calls onto the telephone network themselves. You need somebody in an authoritative position to allow that. So that is the model that we're trying to portray here. We also want to add the ability to do this in an automated way. So the proposal right now is to use ACME, which is another IETF standard being used by folks, sort of notably Let's Encrypt uses ACME, and it provides a nice way that in the past, if certificates are sort of CSRs occur in a little bit of a manual way where you submit things. Email is often used to send certificates back. ACME provides a nice RESTful interface that can essentially automate the whole process, and that's good for both consistency of the process itself, as well as the ability to, for example, Let's Encrypt. It generally has the policy that you can renew your certificates, rotate your certificates every 90 days, which in general is a good practice. So we'd like to incorporate some of that practice as well. So I think the initial definition will incorporate some of those things. We'll have to evolve to support TN level certificates, as well as the ability to potentially revoke things as well if you're a bad actor. So as I mentioned, we may start with manual methods on the very, very initial deployments, but we'd like to move very quickly to adopt the ACME-based certificate management protocols. And we'd also like to put a security framework around that. So from an administration point of view, we need to make sure that you're a valid user of these services to get certificates. And that may correspond to more policy-related things like telephone number management. And as I mentioned, also sort of puts you in the auspices if you're doing bad things. You may have the risk of getting revoked using things like OCSP and other more advanced certificate management techniques. And we proposed this model into the Shaken Certificate Framework document of the sense of a governance and administration, and for telephone authorities and service providers that utilize those services, there'll likely be some key exchange that would grant them access through standard OAuth style security practices to authenticate the initiator of those requests. So from a next steps point of view, the STIR documents just finished working group last call in IETF. In fact, I'll be updating the passport document today, and 4474 BIS will be, the final document will be, with all the comments included, will come out today. The SIP profile document has already gone into letter ballot at the beginning of this month. The certificate management framework document is targeted for the end of the year. The robocalling strike force will actually issue their report October 26th, so that will provide more insight into what the industry is doing as well. And we've also done some initial interoperability tests at events like SIPIT and within ATIS as well. There's a test bug focus group. And I'll just plug Comcast has developed a open source implementation, so if there's any folks interested in playing around with this technology or getting more familiar with it, we certainly encourage you to check that out. It's a server-side implementation of the STIR authentication service and verification service, and we'll be evolving that as time goes on as well. So that's the end of my talk. I guess it's pretty much out of time, so please find me if you have any questions. I'd be happy to discuss this.